me say the word graph, so I better start off with my handy dandy tool, Matplotlib. No, of course not. We're not here to talk about graphs in the form of visualizations. We're here to talk about graphs in the form of a data structure that can solve problems that we might have. And so we'll start by importing Matplotlib, but we'll import Matplotlib in order to visualize the core, the star of what we want to talk about, this NetworkX graph object. Here we can see if we print this out, the repr for this is not that great. It tells us, it doesn't have the angle brackets like it's supposed to, and it doesn't really tell us that much. It says it's a graph with 4 nodes and 3 edges, whatever that might be. But if I draw this and I show this using Matplotlib, you can see, oh, that's what he's talking about. He's talking about entities, what we call nodes or vertices, that are connected in some fashion, connected by links or connections or edges. And here we can see this is our graph with 4 nodes and 3 links, 3 edges. Now, before we get any further, I want to go through just a little bit of terminology. The circles there were nodes, the lines there were edges, but there's a little bit more than just that. We need to talk about not only nodes and edges, but the nature of these graphs, things like directed versus non-directed graphs. Here, if you zoom in, you might be able to see that these edges, and let me see if I can redraw this for you. You'll see that these edges have a little bit of an arrow on one side of them. This is what we call a directed graph. A directed graph indicates that 2 elements are connected, but that connection is one way. If this is a graph of our friendships, this means that I'm friends with somebody, but they don't quite reciprocate that friendship. Distinct from directed graphs, what we saw previously was an undirected graph, a directed graph where everything is symmetric. We can think that an undirected graph is basically a directed graph where you've just doubled all of the edges. You're pointing them in both directions. When we talk about directed graphs, we can also talk about cyclic graphs. Here, we can see a graph, and this node is connected to this node, is connected to this node, is connected back to this node. There's a cycle. There's some path in this graph that ends up where it started. Here we have a directed graph that happens to have a cycle in it. The cyclical nature of a graph comes up quite a bit when we look at the different algorithms. You may have heard people talk about things like DAGs, which is a shorthand term for directed acyclic graph. It happens to be the case that a lot of the common graph algorithms that you might use don't really work, or they have failure modes when you give it cycles. They don't track those cycles appropriately, or there's some assumption they make that there are no cycles. And so it's very often that when we start with a graph problem, we say we have a directed graph, and there are no cycles in it. It's a directed acyclic graph. But a directed acyclic graph can also refer to something slightly related, something that you may have heard about before, the idea of a tree. Here we have some nodes. This node is connected to this node, which is connected to this node on the left-hand side and this node on the right-hand side. What is the difference between a graph and a tree? Well, a tree is basically some node that's connected to another node that's connected to another node that's connected to another node. It's a directed graph because there's a clear relationship between the parents and the children. There are no cycles in it. And we may even further specify that that tree has a fixed number of connections, a fixed number of outward edges. It has a fixed number of children. If we're talking about, for example, a binary tree where each parent can have at most 2 children, or when we're talking about things like a complete binary tree where we have some guarantee that almost everybody has exactly 2 children and there's only maybe 1 node that's missing any children. It's not that some have some children, some have 1, some have 2, but there's some completeness there. So that's a little bit of the terminology that we can get through. Finally, when we talk about a graph, if it's a directed graph, we may, and especially if it's a tree, we may want to distinguish between the nodes at the very top, the ultimate most parents, and the nodes at the very bottom, the ultimate most children, the ancestors, the predecessors. At the very top, the ultimate most ancestor, the parent that is the parent of everything, is often referred to as the root, and the children, who themselves have no children, are often called the leaves, if we're using the tree terminology. But I want to take this a little bit further, and I want to talk about what a node is really. Because that terminology may be very familiar to you, but it may not always be clear what constitutes a node or an edge. You may have even seen mathematically people refer to a graph as a set of 2 entities, one which is a set of the vertices and one which is the set of the edges. And the edges are some tuple of some entity from here and some other entity from here. And this is a very common formulation that people use, at least in the mathematical literature, for what a graph is. Well, If we think about it from the perspective of the specific tool that I'm using here, that is NetworkX, a node is some entity that I can interact with. It's some Python object. It has direct representation. And so here I have a data class, and it is serving as my node of my graph. And so here I have node A connected to node B and node A connected to node C in this directed graph, where each of those nodes are some Python class. Now note that this data class is mutable. Therefore, I am hashing on the ID of this, not on its equality, not on its value. And this is something that comes up every so often when we talk about the relationship between mutability and hashability. Namely, in this particular example, we don't really need to be able to pick out nodes randomly. There's probably some designated node, like a starting point, and some designated node, the stopping point. Maybe a source and a sink is how we may refer to them if we're talking about flow problems. And so we can see that, I can hash on the identity of a mutable type if I don't need this random access, if I don't need this disintermediate access. But let's see if we can make this a little bit more concrete. One of the canonical examples that comes up when we talk about graphs is mapping things like flights. And so here you can see a graph. It's a directed graph going from New York to San Francisco with a weight. There's some information associated with that edge. But note that the edge itself does not have direct representation in NetworkX. It may have some data tagged on it, but there's no Python object representing that edge beyond just a tuple of the two nodes. Well, here you can see there's a flight from New York to San Francisco. This is a directed graph. So just because I can fly to London for some price doesn't mean that I can fly back home from London for that price. In fact, this is very realistic because it's more expensive often to fly in one direction than the other. And there's also another path from New York through Phoenix Sky Harbor to San Francisco. And one of the questions I may ask about this is, what's the cheapest way with the fewest number of stopovers to get to San Francisco? And you can see these two paths cost the same, but one has a stopover. And so I might want to do some optimization to find the best flight. Well, one of the things when you look at an example like this that you might realize is a little bit artificial is there's not one ticket between New York and San Francisco. There are multiple. Even if we strict ourselves to one particular airline, one particular time of day, there's at least a first-class ticket, a business class ticket, maybe even a premium economy ticket, and an economy ticket. And between you and me, I don't fly economy anymore. It's only business or first class, and so I only care about these two fare classes. I actually want to model this as a MultiDiGraph, a graph where two nodes can be connected by multiple edges. One, which represents the business fare, and one which represents the first class fare. It might be worth upgrading, actually. It's only $100 more here. The problem with the MultiDiGraph, especially in NetworkX, is if I use something like shortest path to figure out what is the shortest path from New York to Tokyo Narita, knowing that I can fly in business class or I can fly in first class for the first leg, and I can only fly in business class for the second leg, well, it tells me what the nodes were, what the stopovers were, but it didn't tell me what the fare was. See, it gives me each of the stopovers, but not the fare. So I don't know, is it better for me to fly in business class? Is it better for me to fly in first class? And one thing that we'll talk about later is I probably can't split the fare in that fashion, or at least they're probably going to charge me for a first class fare, even if they don't really have first class seats on this flight. And so there may be some additional rules that I need to figure out how to fit into shortest path that I simply won't be able to. But fundamentally, with this MultiDiGraph, one of the problems, at least with our NetworkX modeling, is we actually kind of care which edge is taken because there's multiple possible edges. But this is a fairly easy thing to resolve. And for tools that do not model a MultiDiGraph, one of the things that you can think about is you do not have to import iSlice and T from the itertools module. You do not have to create NYs. You do not have to NYs these and then back convert from these what the actual edges are, because one of the things that you could actually do here is, instead of modeling multiple paths from A to B as two nodes with two edges, you could create a node that represents the connectivity itself, and instead model from A to B as four distinct entities: A, B, and this intermediary between them, and this intermediary. And what you can think is that means that the edge itself does not actually have to have any data. It can just be information about the connectivity with nothing else required at all. All the actual data of the example can be stored on the nodes, because this is a completely equivalent modeling, even though from a NetworkX perspective, most of the NetworkX stuff which looks at edge data is going to look at edge data in a particular place, but generally this is a completely equivalent modeling. which means that we can choose, instead of modeling this as a multi-digraph, we can choose to model this as a normal digraph where each of the fares themselves are the actual intermediaries. So we go from New York to San Francisco via this fare, from New York to San Francisco via this fare. And one of the tricks that we might do in order to encode that you can't switch fares is we might change what the connectivity is. We might say that this is to San Francisco under a business class fare as a layover, and this is then the connection there. So we might end up not having one entity, one node per destination, but one node per destination for a particular possible fare, a particular route. The downside of this is that we may discover that tools like NetworkX aren't really going to be able to naively make use of this. We're going to have to recode some of the algorithms that we have. It's going to be a little bit of a pain, but from a pure modeling perspective, one of the things that I want to draw your attention to is the node itself is the interesting thing in the graph. The connectivity, the edge, is really just the connectivity. And algorithms that talk about edge data can easily be converted to algorithms that just talk about data that exists on the node itself, so that the edge itself never really needs to have a first-class modeling. Talking about modeling, one thing that I want to draw your attention to is, when we talk about graphs, we're not just talking about the canonical airline fare problems, things like that. We might discover that graphs show up much more frequently in our day-to-day work, even if our day-to-day work is more about building workflows, doing business analyses. Because if you think about it, any business workflow is probably conceptualized by the business user as a flowchart. And that flowchart is probably a directed acyclic graph. And you can model that flowchart in your code as a NetworkX digraph. So if you have some flowchart that, for example, represents some data that goes through some states, like any validation of some data, or perhaps some business rule or business process, it can be modeled as a graph. And you can see here that I'm modeling as a graph, not using NetworkX, but using a very simplistic modeling where each of the nodes are just strings that are collected together in this list, and each of the transitions, each of the edges, are just dictionaries containing dictionaries with some edge data as the result of this. And this is actually very close to what the underlying NetworkX model looks like. And I can then create a little executor that executes the transition through this particular state machine in order to compute this. This may be very useful because it gives me a first-class modeling of where the process might fail. So if this is, for example, an approval process in a company, I know, oh, what blocks this approval is a dependency on an approval from this manager, for an approval for this manager, an approval for this manager. And I might want to be able to visualize this and have a big red circle saying, oh, it looks like the vice president hasn't signed off yet. That's why this ticket hasn't been actioned yet. But an important thing for us to note is there are many possible modelings of a graph. This is one modeling of a graph that implements some sort of code flow. This is a code graph or a control flow graph. Another possible modeling is as a coroutine. And so this code here implements a very similar mechanism, but the graph is implicit on the control flow mechanisms within this code. Now, I don't want to go into this example in too much depth, but it is a very powerful idea when you realize that the code itself that you write, the functions, the coroutines that you write themselves, are themselves graphs, which do give you information about what state you're in, except you'll have to infer that from, for example, the frame f last instruction.